Tree decomposition of graphs. In the previous two sections, we've seen how particular NP-hard problems, specifically maximum weight independent set and graph coloring, can be solved when the input has a restricted structure. When you find yourself in this situation, able to solve an NP-complete problem in a reasonably natural special case, it's worth asking why the approach doesn't work in general. As we discussed in section 10.2 and 10.3, our algorithms in both cases were taking advantage of a particular kind of structure, the fact that the input could be broken down into subproblems with very limited interaction. For example, to solve a maximal weight independent set on the tree, we took advantage of a special property of rooted trees. Once we decided whether or not to include a node U in the independent set, the subproblems in each subtree become completely separated. We can solve each as though the others did not exist. We don't encounter such a nice situation in general graphs where there might not be a node that breaks the communication between subproblems in the rest of the graph. Rather, for the independent set problem, decisions we make in one place seem to have complex repercussions all across the graph. So we can ask a weaker version of our question instead for how general a class of graphs can we use this notion of limited interaction, recursively chopping the input using small sets of nodes to design efficient algorithms for a problem like maximal weight independent set. In fact, there is a natural and a rich class of graphs that supports this type of algorithm. They are essentially generalized trees, and for reasons that will become clear shortly, we will refer to them as graphs of bounded tree widths. Just as with trees, many NP-complete problems are tractable on graphs of bounded tree widths, and the class of graphs of bounded tree widths turns out to have considerable practical value, since it includes many real-world networks on which NP-complete graph problems arise. This type of graph serves as a nice example of finding the right special case of a problem that simultaneously allows for efficient algorithms and also includes graphs that arise in practice. In this section, we define the tree widths and give the general approach for solving problems on graphs of bounded tree widths. In the next session, we discuss how to tell whether a given graph has bounded tree widths. Defining tree widths, we now give a precise definition for this class of graphs that is designed to generalize trees. The definition is motivated by two considerations. First, we want to find graphs that we can decompose into disconnected pieces by removing a small number of nodes. This allows us to implement dynamic programming algorithms of the type we discussed earlier. Second, we want to make precise the intuition conveyed by tree-like drawings of graphs in Figure 10.5b. We want to claim that the graph G pictured in this figure is decomposable in a tree-like way along the lines that we've been considering. If we were to encounter G as it is drawn in Figure 10.5a, it might not be immediately clear why this is so. In the drawing in Figure 10.5b, however, we see that G is really composed of 10 interlocking triangles, and 7 of the 10 triangles have the property that if we delete them, then the remaining of G falls apart into disconnected pieces that recursively have those interlocking triangle structures. That recursively have those interlocking triangle structures. The other three triangles are attached at the extremities. And deleting them is sort of like deleting the leaves of a tree. If we view it not as being composed of 12 nodes, as we really would, but instead as being composed of 10 triangles. Although G clearly contains many cycles, it seems intuitively to lack cycles when viewed at the level of these 10 triangles, and based on this, it inherits many of the nice decomposition properties of a tree. We will want to represent the The tree-like structure of these triangles is by having each triangle correspond to a node in the tree, as shown in figure 10.5c. Intuitively, the tree in this figure corresponds to this graph, with each node of the tree representing one of the triangles. Notice, however, that the same nodes of the graph occur in multiple triangles, even in triangles that are not adjacent in the tree structure, and there are edges between nodes in triangles very far away in the tree-like structure. For example, the central triangle has edges to nodes in every other triangle. How can we make the corresponding between the tree and the graph precise? We do this by introducing the idea of a tree decomposition of a graph G, so named because we will seek to decompose G according to a tree-like pattern. Formally, a tree decomposition of G equals to V consists of a tree T on a different node set from G, and a subset Vt, which is a subset equals to V, associated with each node T of capital T. We will call these subsets Vt the pieces of the tree decomposition. We will sometimes write this as the ordered pair T and the set Vt such that little t is in capital T, the tree capital T, and the collection of pieces, the set V little t such that little t is in capital T, must satisfy the following three properties. Node coverage. Every node of G belongs to at least one piece Vt. Edge coverage. For every edge E of G, there is some piece Vt containing both ends of E. Coherence. Let T1, T2, and T3 be three nodes of T, such that T2 lies on the path from T1 to P3. Then, if a node V of G belongs to both Vt1 and Vt3, it also belongs to Vt2. It's worth checking that the tree in figure 10.5c is a tree decomposition of the graph using the 10 triangles as the pieces. Next, consider the case when the graph G is a tree. We can build a tree decomposition of it as follows. The decomposition tree T has a node Tv for each node V of G and a node Te for each edge E of G. The tree T has an edge Tv Te when V is an end of E. Finally, if V is a node, then we define the piece VTV equals to the set Vt, and if E equals to UV is an edge, then we define the piece Vt equals to the set UV. We can now check that the three properties in the definition of a tree decomposition are satisfied. Properties of a tree decomposition. If we consider the definition more precisely, we see that the node coverage and edge coverage properties simply ensure that the collection of pieces corresponds to the graph G in a minimal way. The crux of the definition is in the coherence property. While it is not obvious from its statement that coherence leads to tree-like separation properties, in fact it does so quite naturally. Trees have two nice separation properties closely related to each other that get used all the time. One says that if we delete an edge E from a tree, it falls apart into exactly two connected components. The other says that if we delete a node T from a tree, then this is like deleting all the incident edges. And so the tree falls apart into a number of components equal to the edge of T. The coherence property is designed to guarantee that separations of T of both these types correspond naturally to separations of G as well. If a T' is a subgraph of T, we use the Gt' to denote the subgraph of G induced by the nodes in all pieces associated with nodes of T'. That is the set the unions of Vt such that the union is for all the index of little t which is in capital T'. First, we consider deleting a node little t of capital T. 10.13. Suppose that capital T minus small t, little t, has components t1, t2, t3 until td. Then the subgraphs g t1 minus vt, g t2 minus vt, g t3 minus vt, and so on until gtd minus vt have no nodes in common, and there are no agencies between them. Proof. We refer to figure 10.6 for a general view of what the separation looks like. We first prove that the subgraphs gti minus vt do not share any nodes. Indeed, any such node v would need to belong to both gti minus vt and gtj minus vt for some I which is not equals to j, and so such a node v belongs to some piece vx with x in ti and to some piece vy with y in tj. Since t lies on the xy path in t, it follows from the coherence property that v lies in vt and hence belongs to neither gti minus vt nor gtj minus vt. Next, we must show that there is no h e equals to uv in g with one end u in subgraph gti minus vt and the other end v in gtj minus vt for some j which is not equals to I. If there were such an h, then by the h coverage property, there would need to be some piece vx containing both u and v. The node x cannot be in both the subgraphs ti and tj. Suppose by symmetry, x is not in ti, node u is in the subgraph gti, so u must be in a set vy for some y in ti. Then the node u belongs to both vx and vy, and since t lies on the xy path in t, it follows that u also belongs to vt, and so it does not lie in gti minus vt as required. Proving the age separation property is analogous. If we delete an age xy from t, then t falls apart into two components, x containing little x and y containing little y. Let's establish the corresponding way in which g is separated by this operation. 10.14. Let x and y be two components of t after the deletion of the h xy. Then deleting the set vx intersect vy from v disconnects g into the two subgraphs gx minus the intersection between vx and vy and gy minus the intersection between vx and vy. More precisely, these two subgraphs do not share any nodes, and there is no h with one end in each of them. Proof. We refer to figure 10.7 for a general view of what the separation looks like. The proof of this property is analogous to the proof of 10.13. One first proves that the two subgraphs gx minus the intersection between vx and vy and gy minus the intersection between vx and vy do not share any nodes, by showing that a node v that belongs to both gx and gy must belong to both vx and to vy, and hence it does not lie in either gy minus the intersection between vx and vy or gx minus the intersection between vx and vy. Now we must show that there is no h equals to uv in g with one and u in gx minus the intersection between vx and vy, and the other end v in gy minus the intersection between vx and vy. If there were such an h, then by the h coverage property there would need to be some piece vz containing both u and v. Suppose by symmetry that z is in x. Node v also belongs to some piece vw for w in y. Since x and y lie on the wz path in t, it follows that v belongs to vx and vy. Hence, little v is in the intersection between vx and vy, and so it does not lie in Gy minus the intersection between Vx and Vy as required. So tree decompositions are useful in that the separation properties of T carry over to G. At this point, one might think that the key question is, which graphs have tree decompositions? But this is not the point. For if we think about it, we see that of course every graph has a tree decomposition. Given any G, we can let T be a tree consisting of a single node T, and let the single piece Bt be equal to the entire node set of G. This easily satisfies the three properties required by the definition, and such a tree decomposition is no more required by the definition than the original graph. The crucial point, therefore, is to look for a tree decomposition in which all the pieces are small. This is really what we are trying to carry over for trees by requiring that the deletion of a very small set of nodes breaks apart the graph into disconnected subgraphs. So we define the width of a tree decomposition T and the set Vt to be 1 less than the maxima size of any piece Vt. That is, the width of T and the set Vt is equals to the maxima of the size of Vt, where the maxima taken among all possible little t, then minus 1. We then define the tree width of G to be the minimum width of any tree decomposition of G. Due to the age coverage property, all tree decompositions must have pieces with at least 2 nodes, and hence have tree widths at least 1. Recall that our tree decomposition for a tree G has a tree width 1, as the sets Vt each have either 1 or 2 nodes. The somewhat puzzling minus 1 in this definition is so that trees turn out to have tree width 1 rather than 2. Also, all graphs with a non-trivial tree decomposition of tree width W have separators of size W, since if xy is an edge of the tree, then by 10.14, deleting Vx intersect Vy separates G into 2 components. Thus, we can talk about the set of all graphs of tree width 1, the set of all graphs of tree width 2, and so forth. The following fact establishes that trees are the only graphs with tree width 1, and hence our definitions here indeed generalize the notion of a tree. The proof also provides a good way for us to exercise some of the basic properties of tree decompositions. We also observe that the graph in figure 10.5 is thus, according to the notion of tree widths, a member of the next simplest class of graphs after trees. It is a graph of tree width 2. (10.15) A connected graph G has a tree width 1 if and only if it is a tree. Proof. We have already seen that if G is a tree, then we can build a tree decomposition of tree width 1 for G. To prove the converse, we first establish the following useful fact. If H is a subgraph of G, then the tree width of H is at most the tree width of G. This is simply because given the tree decomposition T and the set Vt of G, we can define a tree decomposition of H by keeping the same underlying tree T and replacing each piece Vt with a Vt intersect H. It is easy to check that the required 3 properties still hold. The fact that certain pieces may now be equal to the empty set does not pose a problem. Now suppose by way of a contradiction that G is a connected graph tree width 1 that is not a tree. Since G is not a tree, it has a subgraph consisting of a simple cycle C. By our argument from the previous paragraph, it is now enough for us to argue that the graph C does not have tree width 1. Indeed, suppose it had a tree decomposition T and the set Vt in which each piece has size at most 2. Choose any two edges uv and u'v' of C. By the edge coverage property, there are pieces Vt and Vt' containing them. Now, on the path in T from little t to little t prime, there must be an edge xy such that the pieces Vx and Vy are unequal. It follows that the set of Vx intersect Vy is less than or equals to 1. We now invoke 10.14, defining x and y to be the components of T minus the edge xy containing x and y. Respectively, we see that deleting Vx intersect Vy separates C into Cx minus the intersection between Vx and Vy, and Cy minus the intersection between Vx and Vy, and the other contains the set u'v' minus the intersection between Vx and Vy. But it is not possible to disconnect a cycle into two non-empty subgraphs by deleting a single node, and so this yields a contradiction. When we use tree decompositions in the context of dynamic programming algorithms, we would like, for the sake of efficiency, that they not have too many pieces. Here is a simple way to do this. If we are given a tree decomposition T and the set Vt of a graph G, and we see an edge xy of T such that Vx is a subset equals to Vy, then we can contract the edge xy, folding the piece Vx into the piece Vy, and obtain a tree decomposition of G based on a smaller tree. Repeating this process as often as necessary, we end up with a non-redundant tree decomposition. There is no edge xy of the underlying tree such that Vx is a subset equals to Vy. Once we've reached such a tree decomposition, we can be sure that it does not have too many pieces. 10.16. Any non-redundant tree decomposition of an n-node graph has at most n pieces. Proof. We prove this by induction on n, the case n equals to 1 being clear. Let's consider the case in which n is greater than 1. Given a non-redundant tree decomposition, T and the set Vt of an n-node graph, we first identify a leaf little t of capital T. By the non-redundancy condition, there must be at least one node in Vt that does not appear in the neighboring piece, and hence, by the coherence property, does not appear to any other piece. Let U be the set of all such nodes in Vt. We now observe that by deleting little t from capital T and removing Vt from the collection of pieces, we obtain a non-redundant tree decomposition of G minus U. By our inductive hypothesis, this tree decomposition has at most m minus the size of U, which is less than or equals to n minus 1 pieces, and so T and the set Vt has at most n pieces. While 10.16 is very useful for making sure one has a small tree decomposition, it is often easier in the course of analyzing a graph to start by building a redundant tree decomposition and only later condensing it down to a non-redundant one. For example, our tree decomposition for a graph G that is a tree built a redundant tree decomposition, it would not have been as simple to directly describe a non-redundant one. Having thus laid the groundwork, we now turn to algorithmic uses of tree decompositions. Dynamic programming of a tree decomposition. We began by claiming that the maximum weight independent set could be solved efficiently on any graph for which the tree width was bounded. Now it's time to deliver on this promise. Specifically, we will develop an algorithm that closely follows the linear time algorithm for trees. Given an n-node graph with an associated tree decomposition of width w, it will run in time big O of f of w times n, where f dot is an exponential function that depends only on the width w, not on the number of nodes n. And, as in the case of trees, although we are focusing on maxima weight independent set, the approach here is useful for many NP-hard problems. So, in a very concrete sense, the complexity of the problem has been pushed off the size of the graph and into the tree widths, which may be much smaller. As we mentioned earlier, large networks in the real world often have very small tree widths, and often this is not coincidental, but a consequence of the structure or modular way in which they are designed. So if we encounter a 1000 node network with a tree decomposition of width 4, the approach discussed here takes a problem that would have been hopelessly intractable and makes it potentially quite manageable. Of course, this is all somewhat reminiscent of the vertex cover algorithm from section 10.1. There, we push the exponential complexity into parameter k, the size of the vertex cover being sought. Here, we did not have an obvious parameter other than n lying around, so we were forced to invent a fairly non-obvious one, the tree widths. To decide the algorithm, we recall that we did for the case of a tree T. After routing T, we built the independent set by working our way up from the leaves. At each internal node U, we enumerated the possibilities for what to do with U, include it or not include it, since once this decision was fixed, the problems for the different subtrees below U became independent. The generalization for a graph tree with a tree decomposition T and the set of Vt of width W looks very similar. We root the tree T and build the independent set by considering the pieces Vt from the leaves upward. At an internal node T of little t of capital T, we confronted the following basic question. The optimal independent set intersects the piece Vt into some subset U, but we don't know which set U it is. So we enumerate all the possibilities for this subset U, that is, all possibilities for which nodes to include from Vt and which to leave out. Since Vt may have size up to W plus 1, this may be 2 to the W plus 1 possibilities to consider, but we now can exploit two key facts. First, that the quantity 2 to the W plus 1 is a lot more reasonable than 2 to the n than W is much smaller than n. And second, that once we fix a particular one of these 2 to the W plus 1 possibilities, once we have decided which nodes in the piece Vt to include, the separation properties 10.13 and 10.14 ensure that the problems in the different subtrees of T below little t can be solved independently. So while we settle for doing brute force search at the level of a single piece, we have an algorithm that is quite efficient at the global level when the individual pieces are small. Defining the subproblems. More precisely, we root the tree capital T at a node R. For any node little t, denote the subtree rooted at with the index. Recall that T denoted the subgraph of the tree indexed by the nodes in all pieces associated with all pieces associated with the notation of T. We will also write notation of capacity. We will write subset nodes of FT for a subset the total weight of nodes in U. That is total weight equals to the summations of WU. That is W of little equals to the summations of WU. We define a set of subproblems for each subtree T. We define one corresponding to each possible subset U of VT. One that may represent the intersection of the optimal solution with VT. Thus, for each independent set U which is subset equals to VT, we write FT of U to denote the maximal weight of an independent set S in GT, subject to the requirement that S intersect VT VT is equals to U,
subject to the
quantity
requirement
ft
that
of U
S
is
undefined
undefined
if
if
U
U is not
is
an
equals to
independent
U.
set,
The
since in
quantity
this case
ft
we
of
know
U
that
is
U cannot
undefined if
represent
U
the
is
intersection
not an
of the
independent
optimal
set.
solution
Since in
with
this case we
VT.
know that U
There
cannot
are at most
represent
2 to
the
the plus
intersection
one
of
subproblems
the optimal
associated
solution
with each
with
node
VT.
little t of capital T.
There
Since
are at
this is
most
the
2 to
maximum
the
possible
plus
number
one
of independent
subproblems
subsets
associated
of
with
VT.
each node little t
By
of capital T.
10.16,
Since
we
this is
can
the maximum
assume
possible
we are
number of
working with a
independent
tree
subsets
decomposition
of VT.
that has at
By
most n pieces,
10.16,
and hence there
we
are a
can
total
assume
of
we are
at most
working
2
with
to
a tree
the plus 1
decomposition that
times
has
n
at most n
subproblems
pieces,
overall.
and hence there
Clearly,
are a
if
total
we have
of at
the
most
solutions
2
to
the
all these
plus 1
subproblems,
times
we can
n subproblems
determine the
overall.
maximal weight of an
Clearly,
independent
if we
set
have
in
the
G by
solutions
looking
to
at the
all these
subproblems
subproblems,
associated
we
with
can
the
determine
root
the
R.
maximal weight of
We
an
simply
independent
take the
set in
maxima
G by
over
looking
all
at the
independent
subproblems
sets U,
associated
which is
with the
subset
root
equals
R.
to
We simply
VR,
take the
or
maxima
of
over all
FR
independent
of U.
sets U, which is subset equals to VR,
八
of
傻小
FR of U. Building up solutions. Now we must show how to build up the solutions to these subproblems via a recurrence. It's easy to get started when T is a leaf. Ft of U is equals to W of U for each independent set U, which is a subset, or equals to Vt. Now suppose that T has children, T1, T2, T3, until Td, and we have already determined the values of Fti of W for each child Ti and each independent set W, which is subset equals to Vti. How do we determine the value of Ft of U for an independent set U, which is subset equals to Vt? Let S be the maxima weight independent set in VGT subject to the requirement that S intersect Vt is equals to U. That is, W of S is equals to Ft of U. The key is to understand how this set S looks when intersected with each of the subgraph GTI as suggested in figure 10.8. We let Si denote the intersection of S with the nodes of GTI. (10.17) Si is a maximum weight independent set of GTI subject to the constraint that Si intersect Vt is equals to U intersect Vti. Proof. Suppose there were an independent set Si prime of GTI with the property that Si prime intersect Vt is equals to U intersect Vti, and W of Si prime is greater than W of Si. Then consider the set S prime, which is equals to S minus Si, then intersect Si prime. Clearly, the weight of S prime is greater than the weight of S. Also, it is easy to check that S prime intersect Vt is equals to U. We claim that S prime is an independent set in G. This will contradict our choice of S as the maximum weight independent set in GT subjected to S intersect Vt equals to U. First, suppose S prime is not independent and let E equals to UV be an H with both ends in S prime. It cannot be that U and V both belong to S, or that they both belong to Si prime, since these are both independent sets. Thus, we must have U in S minus Si prime and V in Si prime minus S, from which it follows that U is not a node of GTI, while V is in GTI minus the intersection between Vt and Vti. But then, by 10.14, there cannot be an H joining U and V. Statement 10.17 is exactly what we need to design a recurrence relation for our subproblems. It states that the information needed to compute Ft of U is implicit in the values already computed for the subtrees. Specifically for each child, Ti, we need to simply determine the value of the maximum weight independent set Si of GTI subject to the constraint that Si intersect Vt is equals to U intersect Vti. This constraint does not completely determine what Si intersect Vti should be. Rather, it says that it can be any independent set Ui which is a subset equals to Vti such that Ui intersect Vt is equals to U intersect Vti. Thus, the weight of the optimal Si is equals to the maxima chosen among the set Fti of Ui such that Ui intersect Vt is equals to U intersect Vti, and Ui is a subset equals to Vti, which is independent. Finally, the value of Ft of U is simply W of U plus these maxima added over the d children of T, except that to avoid overcounting the nodes in U, we exclude them from the contribution of the children. Thus we have 10.18. The value of Ft of U is given by the following recurrence. Ft of U is equals to W of U plus the summations of maxima chosen among all the possible f of Fti of Ui minus the weight of Ui intersect U such that Ui intersect Vt is equals to U intersect Vti, and Ui, which is a subset or equals to Vti, is independent. And after we take the maxima, we do the summation, summing for index I starting from 1 to d. So the overall algorithm now just builds up the values of all the subproblems from the leaves of T upward. To find a maximal weight independent set of G given a tree decomposition T and the set Vt of G, modify the tree decomposition if necessary, so it is a non-redundant root T tree at a node R for each node little t of T in post order if T is a leaf. Then, for each independent set U of Vt, Ft of U is equals to W of U, else for each independent set U of Vt, Ft of U is determined by the recurrence in 10.18. Now, after we break out from the for loop, we return the maximum among the set of Fr of U such that U is a subset or equals to Vr, and U is independent, but we choose the maxima. So an actual independent set of maximal weight can be found, as usual, by tracing back through the execution. We can determine the time required for computing Ft of U as follows. For each of the d children Ti and for each independent set Ui in Vti, we spend time big O of W checking if Ui intersect Vt equals to U intersect Vti to determine whether it should be considered in the computation of 10.18. This is a total time of big O of 2 to the W plus 1 times W times D for Ft of U, since there are at most 2 to the W plus 1 sets U associated with T. The total time spent on node T is big O of 4 to the W plus 1 times W times D. Finally, we sum this over all nodes T to get the total running time. We observe that the sum over all nodes T of the number of children of T is big O of n, since each node is counted as a child once. Thus, the total running time is big O of 4 to the W plus 1 times W times n.